I literally said, be quiet. I'm starting the recording. Okay, so we are in Unit 8. This is Unit 8, Part 1. The packet that I gave you is only 2 parts. We're actually probably going to get into Part 2 today. Part 1 doesn't take the whole class. We are looking at polynomial functions in Unit 8. We are doing very little of Unit 8, actually, just these 2 little sets of notes because we're out of time. So we are not finishing Unit 8, but this is a portion of it, the beginning of it. Part 1 is gonna look at zeros, and this is really just a practice, a review of factoring and understanding what zeros are. I'm hoping Part 1 seems easy. If it does not seem easy because you don't remember factoring, you need to go back and review factoring. We did this. I'm going to show you in It's Learning. Unit 3 is when we reviewed factoring. So if you go back to Unit 3 completed notes, there is the video of the lesson. It says factoring refresher. Okay, and there's the PDF of the completed notes we did to review factoring. Okay, so if you need to go back and look at those notes or watch that video to refresh your factoring skills, you should do that. Okay, we're going to have a practice, a Delta Math, our very last Delta Math on Thursday. And there are some factoring practice questions on there because you've got to be able to factor. Okay, that Delta Math is actually going to open today. It's open right now. If you want to start early, you can. But it's not technically assigned till Thursday, and we'll have the class period Thursday to work on it, and it'll be due next Monday. All right, anywho, back to these notes. We have talked about factoring methods. That's what I just pointed out. And we've talked about polynomial functions. We've talked about their end behavior. Okay, we did that in limit form just in this past unit, Unit 7. When we talked about the limit as x approaches infinity, the limit as x approaches negative infinity and stuff. What the graph was doing. Was it rising or falling on the left and the right? We did the leading coefficient test or the leading term test. We've talked about the turning points on the graph of a polynomial. Those are the maximums and minimums. We talked about absolute versus relative max and minimums. We talked about increasing and decreasing intervals. Okay, we talked about all that was back in Unit 6 before spring break. Okay, so we have talked about different characteristics of polynomials, and what we're going to focus on now are the zeros. Okay, there is a rule. If you know the degree of your function, okay, the degree is the highest exponent. Okay, the degree of your function is the highest number of zeros you could have. Okay, you can have at most n distinct real zeros. And in -1, so 1 less than that, is the maximum number of turning points your polynomial can have. Okay, so if you know, when you identify the n, the degree of your function, which here in this example, the degree is 6, right? That's the highest exponent there. So if you have a n equals 6, that means this could have at most 6 zeros and at most 5 turning points. Does that make sense? It does not mean it will have that many. That's the most it could have. So if you realize that that's the maximum and you go to solve this and you get more than 6 zeros, you know you've made a mistake. Okay? Now, when this one's actually solved or graphed, you can see it has 3 zeros and 3 turning points, which both fall under 6 and 5. So that's good. Does that rule make sense? All right, now this is just a refresher, a reminder of how you can write or word your zeros, your solutions, your x-intercepts. Okay, so if you have a polynomial function f, okay, and we know that c is an x-intercept of that graph, you could write c is a 0 of f. You could write x equals c is a solution, because that means if I plug in a c for x, I get 0 as the output, right? okay? Or if you have it in factored form, it would be x minus c is a factor of the function. Okay, so all of those mean the same thing. They're all different formats of showing that c is an x-intercept. Okay, we can have it in factored form and see that it is the x-intercept. We can have it solved for x, or we can just write c is a 0. Those all mean x-intercept. All right, now we can use the same factoring techniques we reviewed last semester, okay, that you originally learned in algebra and did a lot in algebra 2 again. All those same techniques we can use to factor and solve for zeros. So in this first example, I don't know why it says example 2. I guess this was technically supposed to be example 1. Boop, 1. Okay, so example 2. They first want us to state how many possible zeros, whoa. Okay, so how many possible real zeros and how many possible turning points. Okay, what is the n value here? 3. N is 3. So that means that there are 3 possible real zeros and 2 possible turning points for this function, for this polynomial function. Now they want us to determine all of those real zeros by factoring. So remember your factoring process. You set your function equal to 0. Okay, so I have x cubed minus 5x squared plus 6x equal to 0. I'm trying to find out what x values could I plug in here and it will come out to 0. So to do this, to answer that, I need to factor. Now again, there are different factoring methods. There's greatest common factor. There's difference of squares, difference of cubes. There's just like the quadratic form trinomials where we did box method, grouping, slide divide, guess and check. Okay, so we've got to make sure, again, go back and review those factoring methods. Look at those completed notes if you have forgotten that stuff. What do you notice among all of these terms? So there's definitely a GCF in this one. Okay, so if I take out an x, what is that going to leave me with? So that would be x squared minus 5x plus 6, right? I just divided x out of all of those. Okay, so now factoring needs to just focus on this quadratic. Okay, I've got a quadratic trinomial here that I can factor into 2 binomials. Now, the x factor is still out front, and this is still set equal to 0. That doesn't change. Okay, so I'm asking myself, looking at this trinomial, because the a value is 1, this is a relatively easy one. I would just use guess and check. I wouldn't go through a long process because when a is 1, x squared factors to x times x. And then you just need to know, what does 6 factor to? And the fact that it's positive means they have to be the same sign, right? So either both positive or both negative. And since that middle term is negative, I know it must be negatives. Okay, so a negative times a negative is going to give me the plus, and the negative plus the negative is going to give me the negative. Okay, so what multiplies to 6, positive 6, but adds to negative 5? It's got to be 3 and 2 since they're the same sign. If I did 6 and 1, that would have been negative 7. That wouldn't have worked. So now I've got it completely factored. So then the next step is to split and solve. That means once you have all of each factor only has one x term, you can split it and set each of those factors equal to 0. So this x is equal to 0. X minus 3 is equal to 0. And x minus 2 is equal to 0. This one is already solved, done. What does this come out as when I solve for x here? Yeah, I add the 3 over. So that one is positive 3. And this one is positive 2 because I would have to add the 2 over. Notice the format there that we talked about here. We got it as x equals 3 and x equals 2. And in factored form, it was x minus 3 and x minus 2. So you can see it in factored form, and you can see it as a solution solved for x. Feel okay about that? It was just kind of a factoring review. Okay, factor and solve for x to get your solutions. All right, the next example, again, asks us for the possible number of real zeros and turning points. So we again need to identify our in value, which is what? Okay, this time it is 4. Okay, so n is 4, which means that is the maximum number of zeros, and 3 is the maximum number of turning points. Now, this does not have a GCF, so there's no GCF here, but I'm still going to start the same. Set it equal to 0. And this is not a quadratic. This has x to the 4th, this polynomial, so degree 4. However, the format of it is quadratic form. So that's what this was saying up here. We can find those zeros by using the same factoring techniques we use to solve quadratics if they're in the right format. So here, the degree is double the exponent of this middle term of the trinomial, right? So if this is a 4, a power of 4, power of 2, and then a constant, that's the same format as x squared x and constant, right? So we can use the same factoring method here, and there's no GCF. We're going straight to the trinomial factoring. Okay, so when I do that here, what are the factors of x to the 4th? If that was x squared, we would put x and x, right? So what should I put to get it to be x to the 4th? X squared and x squared, right? Okay, and then I'm asking myself, I'm saying, okay, I need the factors of -4. So one's got to be positive and one's got to be negative, right? Because it multiplies to a negative, that add to -3. So is that going to be 4 and 1 or 2 and 2? 4 and 1. And which one's the positive? Which one's the negative? Yeah, a -4 and a +1 would add to the -3. Okay, now, once you get here, you have 2 options of how to finish solving this. Okay, each factor that I have here has only one x term, right? So I could go ahead and split and solve. I could go ahead and set each factor equal to 0 and solve each of those individually for x, right? My other option, once I get here, is to factor this further, because what some people don't notice right away is that this x squared minus 4, that is a special expression right there. That's a specific type of binomial. Does anybody recognize that? It's the difference of perfect squares, or the difference of 2 squares is, I think, what we called it in our notes. Dots, difference of 2 squares. Difference meaning subtraction, and 2 perfect squares. Okay, when that is the case, you can factor that further. When you factor the difference of 2 squares, you take the square root of each term. So x squared square root is just x, and 4 square root is 2. And there's always a positive and a negative. So I can factor that further and then I still have x squared plus 1 equals 0. And then I'm ready to split and solve. So it's your choice if you want to go ahead and split and solve, or if you want to factor that further to split and solve. And I'm going to point out why it would matter. If I go to solve the x squared plus 1, okay, I would have to subtract the 1 over, right? So that's a -1. And then when I go to take the square root of that, am I able to take the square root of a negative? No, I cannot do that. This one is not going to have a solution because I cannot square root a negative. Okay, so no solution from that factor. Now, over here, when I go to solve, this would be -2, because I would subtract the 2 over, and this one would be +2, right? So I get +2 and -2, so I have 2 zeros. Over here, when I go to solve, I would add the 4, and then I would have to take the square root, and a lot of you would just say x equals 2, and you would be done. And you would be wrong. You would be missing the -2 because a lot of you forget to put a plus or minus in front when you take the square root. So doing the difference of 2 squares to break it apart clearly shows there's 2 answers there, a +2 and a -2. Doing it this way, you just have to be extra careful not to forget that plus or minus. Okay, so both ways we get the same solutions as long as we don't forget the plus or the minus when we take the square root. Does that difference of 2 squares kind of come back to y'all? Okay. All right. So that's some good factoring practice. Now, this will be new, hearing this, what I'm about to say. Repeated roots. Okay, you have repeated roots when a factor appears more than once in the completely factored form of your function. Okay, then we would say that the graph has repeated roots or repeated zeros. Now, what does a repeated root mean for your function? Okay, now it depends how many times it's repeated. Okay, if you have the multiplicity is what we're checking. If you have a 0 that appears an odd number of times, then the graph crosses the x-axis at that 0. So what that looks like, okay, you have whatever your graph is. The 0, the function is actually crossing the x-axis. Your function is going from positive to negative or vice versa, but it is changing signs. It's going from above to below the x-axis. So your function, your f of x, changes sign. Okay. Now, if you have a 0 that appears an even number of times, so a multiplicity of 2 or 4 or 6, okay, then the graph touches the x-axis at that 0. It's just tangent to it, meaning it just grazes it, right? It doesn't actually cross it. So graphically, that would look something like this. It comes and it touches it, but it doesn't cross it. So in that case, your function does not change signs. Okay, it was positive, it touches the x-axis, then it's still positive. Okay, it did not cross the x-axis and change signs. Okay, so if you have a repeated root, you will sometimes be asked about the multiplicity. So if you have a factor that appears more than once, you figure out how many times. What is the multiplicity? Is it even or odd? Because that's going to help you understand the shape of your polynomial. So far, so good? All right, so let's look at this last example. It says to state how many possible zeros, find those zeros, and identify any repeated zeros. Okay, so how many possible? And that's because our degree is 4. So there are 4 possible zeros. Okay, now I'm going to find them by factoring. I'm going to set this equal to 0. And I'm going to factor. Now, what type of factoring can I do first here? Definitely a GCF. What do all of these have in common that I could divide out? An x squared. Now, when my lead term is negative, it makes it a little harder on my factoring. So I'd actually like to change that. How could I change this to a positive? By dividing out the negative, right? So instead of just dividing out x squared, I'm going to divide out negative x squared. So that's going to change all the signs. So this is going, I'm going to be left with positive x squared, positive x, minus 2. If I take each of those and divide out negative x squared, this is what I get. Right? Okay. Now you've got the quadratic trinomial that can factor into 2 binomials. So again, the negative x squared is still out front there. Okay. And how will I factor this trinomial? What does x squared factor to? Okay, and what are the factors of negative 2 that would add to positive 1? Now, immediately I know the signs. If it multiplies to a negative, I've got to have a positive and a negative. Luckily, 2 only has 2 factors, 2 and 1. So I just have to figure out which one do I want to be the positive to add to a positive 1. Yeah, positive 2, negative 1 would add to positive 1. So I've got it completely factored, and I am ready to split and solve. All right, so then the 2 factors here, pretty simple. That's going to be x is negative 2 and x is 1. Okay, now here I want you to understand, if I divide by the negative, still 0, right? Okay, what does x squared technically mean? X times x, right? So this is a repeated root. This is a repeated factor. X is there twice because I could actually split this to x and x, right? And set each of them equal to 0, and I have that x is 0 twice. Or if you think of it as taking the square root, when you take the square root, you normally have to do plus or minus. There's 2 roots, but it's 0. It doesn't really have a sign, so it's not positive and negative 0. It's still just 0, okay? But it's a repeated one. It's repeated twice, okay? and it's even. So this is a repeated root. It's repeated an even number of times, which tells me what? It's only going to touch the x-axis, not cross. Now, these are not repeated, are they? The x plus 2 was only there once, and the x minus 1 was only there once. So those are there an odd number of times, once. So those will cross. So graphically, if you wanted a visual of this to help make sense of what this means that that 0 here, the graph is simply going to come here and touch. It's not going to cross. But at the others, at -2 and at +1, it's going to cross. Now, if I wanted to actually sketch this, I could tell you the end behavior, right? With leading term test. Y'all remember the leading term test? Okay, it's even. So that means they're going the same direction, either both up or both down. And it's negative. So which is it? So both ends are going down, right? The left and right side are both falling. So I know I have to cross these two. So I have to come through and cross, and then I'll have to touch, and then I'll have to cross. So that's the general shape of it. Now these peaks, these maximums may be higher or lower. I didn't bother, I have not gone the step further of finding those. We would do that in this unit later, but we're out of time. So we're just going to focus on where are the zeros. Does that make sense? Okay. Later in Unit 8, if we had more time, we would get into finding some more things about the polynomials, but we don't have time. All right, so that's the end of part 1. I'm going to stop the video here, and but we're going to go ahead and go on to part 2. But I'll do it in a separate video.